I realized that my title was so long I didn't need an outline. It'll just do fine. The things I wanted to talk about here are things that have come up in the workshop. And one is that there's been a couple of times it's come up that the sort of two-timescale approach, which is near and dear to the heart of people who've done geophysical fluid dynamics, somehow doesn't seem to be the appropriate way to go after stratified turbulence. And I kind of agree with the details of what they say, but I sort of don't agree with the philosophy, and I wanted to hold, just kind of maybe restrain everybody in dumping that into the waste paper basket. And the other thing was that this is horizontal spectrum in the stratified turbulence that's been pointed out a couple of times, which seems to be independent of stratification, okay? And Michael McIntyre blurted out, "It's a miracle," when I think it was Jim was talking, or somebody, or Eric or somebody. So I just have a couple of comments about that, and it's very tentative, okay? It's not ready for prime time, but I thought, since these things are supposed to be informal, I'll talk about it anyway. I'm not going to say anything about any real fluid. I'm just going to say the properties of these equations in a kind of triply periodic kind of domain in Fourier space. And you will see that I'm very much kind of a disciple of some of the early stuff from 30, 40 years ago by Craigman. And I want to apply it to this problem, which is rotating stratified turbulence in as simple a context as I can think of. Okay, and so I won't say anything about atmosphere or ocean or anything like that. I'm just talking about these. And I want to right away move it into a normal mode kind of variables. And so this is an old story. You take your variables, which are velocity fields, and B, by the way, is buoyancy for me. And so it's just a density fluctuation. And I want to move it into these guys who are, you simply linearize about a state of rest. In other words, throw away the nonlinear terms and diagonalize. Choose the variables that diagonalize the linear terms. So I have these variables. Here was a diagonal linear term. Formally, at least, I can restore a quadratic nonlinearity in this form. And of course, all the details are in this coupling coefficient. So what happens is I get these eigenvalues here, and I can associate them with frequencies from the form of this, and I got 1, 0 mode, 2 plus or minus a gravity inertial wave frequency. And its dispersion relation for Boussinesq is particularly simple. That's the horizontal component of the wave vector and the vertical component. And the frequency just depends on the angle. The one given by stratification is down here. The one given by the rotation is up there. So now I want to talk about invariance. And we know that there's a quadratic energy invariant in Boussinesq, and it poses no problem. There is also potential vorticity invariant, which is kind of a complicated thing, and it's not quadratic. So typically, for more general equations, it looks like the vorticity dotted with the entropy divided by the density. And in the Boussinesq system, divided by the density bit is really simple. It's just the constant reference density of Boussinesq. So I'll throw away that density and just talk about the numerator here. So there's the absolute vorticity, and that's actually the gradient of the total buoyancy or density, if you like. And the point is that this has got a zero term. This is a constant, that's a constant, this is a constant, that's a flow variable, it's a flow variable. I've got a constant term here, 2 first-order terms of the quadratic term. And I really don't like this quadratic term. So I'm going to find out when can I throw it away. And that's the purpose of this slide. Okay, and so I can throw it away if I can. So I don't need this constant. And I want to say that this PV is it's close to linear if this thing is much smaller than 1. Now I do some very, very standard and non-controversial scaling to get this thing. So this quadratic term is just vorticity dotted with the gradient of the density fluctuations. And I look at all the various terms in that, and I see there's kind of, they fall into 2 categories, this and this. And I'm going to assume something that's non-controversial, which is the vertical scale H is much less than the horizontal scale L as things get stratified. And so that tells me I can throw this term away and just keep that one. And now I need a scale for B is really the scale for that buoyancy fluctuation. And I get that pretty simply from two assumptions. One is pressure is typically of order rho u squared in fluid dynamics. Only I define my pressure without any rho. Okay, so I know that's a bit. Let me just remind you. I didn't put 1 over rho, so my pressure isn't really pressure. So I have u squared for pressure, and I get the order of magnitude of the buoyancy fluctuation by equating the size of the buoyancy term with pressure, okay, the pressure gradient. And this is saying that it's not far from hydrostatic, okay? I'm not saying that it's hydrostatic, I'm just saying it's the order of magnitude of the buoyancy fluctuation. And I think that's sort of built into the Boussardesque approximation. So if I do that, I've got the scale for this guy, and I can similarly, everything I said so far will give you the scales for the linear guys, and I can write this. And I get that, okay? And this is the Froude number, which is the stratification, and the Rossby number, which is the rotation. And it's, in all cases, I find that I can play this game that I want to play, which is that PV is almost linear, and if I square it, I get a quadratic invariant.
What is pi 2 in terms of, pi 1, pi naught through pi 2 are the expansion of what's on the left there?
It's all that stuff, yeah.
Which one is pi 2?
So it's the one that's quadratic and flow variables, okay? So it's that flow variable.
So that's pi 2.
Right.
And the
And
one
these
that's...
are linear, so this
Right.
you take one constant and one flow
Oh, so
variable.
okay, the one with the buoyancies.
So also that line, the next line down, I was confused. You should have a bracket
Yeah.
for the next two pi's. Pi 2 gets divided by both of them together.
It's supposed to be
Yeah,
that. It's
okay.
supposed to be this, right?
Okay,
That's right. It's my second seminar in 2 days, so that kind of glitch is likely to show up. So there's the story. I have to stick with this. Vertical Froude number, small. Now, one of the things that's coming up in recent simulations is that's not true. Okay? And so perhaps that's behind some of this criticism of this approach. Well, but let me get back to that. I don't want to, I'm getting too early, getting ahead of myself. So that's my story. If I get this vertical Froude number small, I don't really have to worry about the Rossby number. I'm okay. Now, here's something else that's completely independent. But if I can use this approximation to throw away that term, I find in my normal mode decomposition, which I just showed you, that only the zero frequency geostrophic mode contributes to the linear part of this invariant. And that becomes, and that's a recurring theme, okay? That's not terribly new. This talk is sort of informal. It doesn't have enough references, I'm afraid, but this is true about the shallow water equations as well. So if you're, no, I think you've forgotten where we are. These are my new variables. This is the equations. And this is the zero frequency mode and the fast modes. Now I'm going to rename them, unfortunately, but this is it last time. I'm just going to rename the zero frequency mode G for geostrophic. And there's my fast modes. And I know that it had the fast linear oscillation term, so I'm going to do a two-timescale analysis here, sort of standard 1970s stuff. And I have a slowly varying part of that, which is the amplitude of the wave, okay? And what I'm showing here is not anywhere near as intimidating as it might look. This is just the slow evolution of the contribution to the energy from these slow modes, geostrophic modes, and the slow evolution of the amplitude of the wave modes, okay? And they both vary on a slow time scale. And this is just, I take a G equation, I multiply by G star, so there's sort of a G in a GK in every one of these things. And the rest of the bracket here is just every combination, GG, GA, AA. And similarly for the A modes, and every time there's an A, there's also an e to the I omega t. So I have stuff like this, okay? And this is the geostrophic modes talking to each other. These are the wave modes talking to each other via three-wave resonances, okay, and that's my, well, I'm getting ahead of myself again. It's only, the effective interactions are the ones where we can get rid of this fast time scale. I think everybody in the audience knows this stuff, so I'm maybe going a little too fast, but I want to get to the meat. I'm looking at my two properties here. One is the resonance, and the other is the conservation. And from the conservation, we have the quadratic invariant, which is the geostrophic energy plus the ageostrophic energy. And as I just said, if you let me play this game, where I just take the quadratic part of the potential entropy, i.e. the linear part of the potential vorticity squared, then I just have the geostrophic modes in here. And that kind of, and it's quadratic. Everybody's quadratic, and so that means each triad interaction conserves. All right? So now I'm almost there. The interactions between waves and vortices, and that's a very loose terminology here, and I'm sure many people would object to it, but let me just use it for brevity, comes from these two kinds of triads, 1A, 2Gs, 2A, 1G. Okay, conservation of this quantity, insofar that the vertical Froude number is small and I can play this game, immediately applies that term as 0. It's simply because you can't get two modes that don't have any of this invariant potential vorticity alter the potential vorticity of that mode, right? If its amplitude goes up, it changes the potential vorticity. So it violates potential vorticity conservation. So that's gone. This one still exists. The geostrophic mode is required, but it's a catalyst, and it can allow exchange between ageostrophic modes. The other guy that can effect transfer between is completely off-resonant at all times if all the frequencies are large. Now that's an important thing. So here's my dispersion relation again. This is just the angle that the wave vector makes with respect to the kz axis. And you can see that if I took f and put it to 0, or if I took, then I would have the frequency would vary from n to 0. So it's not true that all frequencies would be large. It's also true that that sort of undermines the whole idea of what I'm doing here. But let me stick to a case where they're all large, for example, and that would be if f and n in some sense are large numbers. In other words, if the Rossby number and the Froude number are both small, then this is wildly off-resonant. This is not 0 because of conservation. This is just moving ageostrophic energy around from one mode to another. This is easy to resonate because of this dispersion relation. It just tells you that that wave vectors k and p are on the same cone, and that you just take any old 0 mode to complete the triad, and you're there. Yeah.
So, when you said Froude number, vertical Froude number is small, you didn't say anything about the Rossby number. So you claim that the Rossby number was small, or you just not saying anything?
I'm not saying anything, but it's there. Okay.
Most people, if you said that's small too, then they would agree with it.
Well, for sure they're going to agree with it. Yeah. I mean, that's the limit where we're.
But you're not implying that.
I mean, well, just from that. Well, that was just from the PV. The quasi-linearity of the PV requires that. Okay. The rest of what I'm saying might require more. I have to think about that more. So, getting back to let's assume the Rossby number and the Froude number are both small, and that both of these interactions are cut off. Then we just have that term there, and these two here. Okay, and I've looked at this numerically, and I mean this is a real monster to try to find resonant interactions. Okay, you should just play around with it on pencil and paper and try to find them. There are very few of them in any kind of numerical grid that any computer today can use. So from the perspective of a numerical simulation, I get this as a kind of approximate dynamics in this limit. Okay, and this is just geostrophic modes. And these become you could show this as just the quasi-geostrophic equations. And then this is this catalytic interaction that I was just talking about. And I would argue that for sure this analysis is worth the time that it took to describe it. Because if you look at kinetic energy and potential energy in a decaying turbulence simulation, where the initial Rossby and fruit are 1, and as it decays, it goes to lower and lower Rossby and fruit. You look at kinetic energy and potential energy, they look like they're doing the same thing. If you do the decomposition I just told you, you see massive differences. This says log, okay, and that's a decade. So if I just ran this a bit longer, I'd have a decade, an order of magnitude difference in geostrophic and ageostrophic energy. Now the properties of this equation are well known. Chardy in 1971 showed that they have an analogy to two-dimensional turbulence. And that means it has an upscale cascade, and in the limit, in a decaying turbulence context at large Rossby number, energy doesn't decay. And there it is, flattening out. And these guys, I did a little work on them with some statistical mechanics and found out that it's pretty clear they go downscale to equipartition, and that means they hit the dissipation. Okay, so I want to talk about statistical mechanics and what it can do for us, and a bit about what it can't do for us. Now, this is all pretty classical stuff, Creighton 1970s. What you assume is you have a bunch of, we were looking at inviscid truncated equations, all right? So not very realistic fluid model. But we're going to see what happens. Now, there's sort of classic results about this isotropic 3D turbulence if you just look at energy and you forget about the helicity. It goes to equipartition, the same amount of energy in each Fourier mode. And in two-dimensional turbulence, you have energy and entropy, and it's equipartition of a linear combination of those. And I'm going to reason an analogy with 2D, and I'm going to show you it's really very different from 2D. So what you do is, I just want to jump in at this point. We want to maximize entropy, P log P. We want to conserve all the invariants. We want a probability density function that remains normalized. The conservation of the invariance in this particular ensemble is just the conservation of the ensemble average invariant. I'm getting into more detail than I need to. The point is we need invariance of the inviscid truncated set, because this is what we're playing with here. And it's only quadratic invariants that survive Fourier truncation, and that's the reason why I went into that song and a dance about my invariant is almost quadratic if the vertical fruit number is small. And so if you do this and crank through the machinery that Creighton showed us, you get this. And it's kind of interesting. So this is the ensemble average contribution to the energy from a wave mode, and it's equipartition, just like in 3D. And this is the same thing for the geostrophic mode or the slow mode, and you get this linear combination, which looks a lot like the result in 2D, but not quite. And it has the frequency in it.
Peter, what are your lambda 1 and lambda?
Those are Lagrange multipliers, right?
For what invariance?
Sorry?
For which invariance?
Oh, sorry. Lambda 1 is energy. Lambda 2 is potential entropy. Sorry, good question. I should have written that down. Yeah, so that just comes out of this, right? Because one of them looks like a constant times that plus that, and the other one looks like that times that, right? And then you just stick that in there.
So does your system have other invariants, like Sackman type invariants?
If they're not quadratic, I don't care about them, because they're not going to be inherited by this set. They're not going to do anything.
Yeah.
Well, I never went looking for them, so I don't know. Maybe we can think about that later.
It's just a metric conservation in some sense.
Okay, anyway. But can you say the same things for...
I mean, so for example, in 3D, truncated 3D, you do have the Sackman invariant, and that's why you can't get that. That's why the equipartition spectrum can't push all the way into the origin.
Okay. I never had any trouble getting my equipartition spectrum going all the way to the origin.
But you only see that if your box is big enough.
It's 3D, yeah, that's right. My box is never big enough.
And if your box isn't very big, you would see.
Okay. I'm going to make this assumption because I think there's a whole bunch of literature about negative lambdas, okay, and I think it's kind of a waste because you can show rather easily that they're never going to go lambda negative. If you keep the where you put the energy in, so the kind of thought experiment you do is you think about sticking in some energy at some initial scale and then calculating this this equipartition. Okay, that will the particular energy and entropy or potential entropy you put in determine these guys. And you can show that if you put the energy initially very far from the minimum wave number and very far from the maximum wave number, it's guaranteed that you're going to get positive Lagrange multipliers and everything behaves fairly nicely. So I won't even mention these negative energy states. This is isotropic for a mode. So if I do any kind of spectrum involving averages over spheres or cylinders or whatever, it's going to be peaked at the dissipation, so it's going to go downscale. The other thing that's interesting is that that's the frequency of my wave modes. And this is telling me that this particular energy wants to avoid high frequencies. The other thing is, and this is unfortunate, I'm going to get onto no rotation in a second. There it is. Where are we? I'm trying to look for a good copy of my dispersion relation. There it is. Thank you. If I put f to 0, sigma is only a function of k squared times sigma, which gets rid of this, is only a function of horizontal wave number. Oops. Let's go. So one more point, we can go on to stratification. So if you do this with rotation, and you have this problem, you can use these coordinates that Charney introduced, where you just rescale the vertical with n over f. And if you you need to absorb a constant, which is either n squared or f squared, I can't remember, into the Lagrange multiplier, and then this result will look absolutely identical to the geostrophic result and the 2D result. Okay, so I just told you that frequencies, energy wants to go where the high frequencies aren't. And then there's a ton of simulations that kind of are in agreement with this cartoon of Claude Cambon's, which I kind of like. This is the Fourier space. That's kz axis. All the energy is here. But if you look at, this is just stratification by itself. If you look at the high frequencies, they're down here on the k horizontal plane. And then with rotation, you see the opposite. And I haven't really talked about the case of just rotation, but it's very much in agreement with this statement that I just found from statistical mechanics, that at least the vortical energy wants to avoid regions of high frequency. Okay, and then there was this thing all last week, we were talking about critical balance, which is precisely the opposite statement, that the linear time scale and the nonlinear time scale tend to be the same. And it clearly doesn't work for rotation and stratification insofar as the anisotropy of the problem is concerned. Okay, I'll just stop while you read this. It's just, I know I confuse the hell out of people when I start talking about rotation and stratification and I go back and forth, and I'm not going to do that. So that's it for rotation. All right, so now we're going to talk about stratification, and I've talked about that there's two limits. I showed this in Warwick last week that have been discussed a lot in the literature. And one is that the vertical Froude number goes to 0. And I'm also defining a horizontal Froude number. So the vertical Froude number is u over nh. The horizontal Froude number is not surprisingly u over nl. And L is just simply you either use the vertical or the horizontal scale. And I think it's an interesting problem and it's an interesting limit. Perfectly describes well when you start off with isotropic initial conditions and you subject that to stratification. Okay, and then more recent simulations, including mine and others that we've heard about, have sort of suggest that what happens is that the vertical scale collapses in stratified flow, and u over nh is getting bigger as it collapses, and it collapses down to 1, and it stays there. Okay, and so in this case, my asymptotics or my quadratic potential vorticity doesn't work, okay, because I need that to be small. Okay, and the only other thing I want to say is a purely kinematic result, right, is that if we had some kind of scale h that characterizes vertical layering of the flow because of stratification, if I look at wave numbers much smaller than that or scales much bigger than that, my spectrum's got to be flat, okay? It's just because just think of this as Z. If this looks like this and it just goes rapidly to 0 beyond some scale, then the transform looks like this. And if HKZ is much smaller than 1, in other words, KZ is much smaller than 1 over H, in other words, we're talking about scales bigger than, then this just goes out and this looks like a constant. So the spectrum is flat, okay? And the other thing is, can I resuscitate, even in this limit, can I resuscitate some of what I'm saying by introducing a kind of a spectral Froude number, okay? Because here I'm saying it's flat in the large scales. And if I have flat, for example, I'm going to get a Froude number that goes as kz to the 3 halves. So it's small at low kz, and it goes up to 1, presumably, and something else happens. Okay, so I think I've emphasized this enough to be considered reasonably honest. Let's just do it anyway and see what we get. And what I've done here is average my modal energy, and this was just a minute ago, it was k squared times sigma squared. And that just turns out to be k squared, and I've absorbed an n into the definition of lambda. I apologize for that, it's a bit loose, but I just thought I didn't want to write n squared kh squared, but the point is it's in there. And then these are the wave modes. I think they switched positions since the last one. And I could see that this reaches a peak if lambda 1 and lambda 2 are positive, and believe me, for any kind of reasonable initial conditions they are. Then this reaches a peak that's here. Okay, now let's stop there, and let me tell you a bit about Creighton in 1967. If we just put this to 0 and get rid of that, then we have more or less, exactly the same result as Creighton got in 2D. All right, and what he did is what I'm about to do in the next slide for this problem. He did this problem with that 0, and what he found was, if you look at something like this, he found that k peak goes like this, k max times e to the minus k max squared over 2ki, and I haven't defined ki, I see, which is the ratio of energy, the wave number you get from the entropy to the energy. Okay. So if you're thinking about injecting energy at some scale and kind of close to a delta function at t equals 0, then obviously that's where the delta, it's going to be at that scale. Okay, so that's sort of determined by your initial conditions, but he just looked at this and said, what happens if I go to the continuous limit, I take k max out to infinity? Well, k peak goes to 0, and that's why he said there is an inverse cascade of energy. Okay, so now I'm going to do the calculation for my problem. All right, and it starts off, this is what graduate students are for. It starts off with integrating these guys, okay? And these are the integrals. So that's energy. And this guy comes from the geostrophic mode, which has got the lambda 1 and lambda 2. And that comes from the wave modes, which just have lambda 1. And we have to integrate the entropy as well, the quadratic part of the potential entropy. And then I do this thing, and unfortunately my k, is because of my unfortunate notation, I got something analogous to this, but I have a problem. Dimensionally, I need an n squared in mind. But it's the same thing. So if you look at this equation, let's write it like k squared, n squared, sorry, k, what am I doing? K, My brain's just gone. Sorry, I just want to square this thing, okay? So it's k squared times n squared e equals v. Just write that down, plug these things in, it gives you this. And this one has one root that's of interest, okay? I want to consider the injection scale to be much, much smaller than the maximum wave number. So I can throw that away, and I get log of 1, which is 0. And I want this to be 0, and I have two choices, and that choice is really not very interesting. And the one that's interesting is this, x equals a half. And if now that x is just this, which tells me the ratio of lambda 2 over lambda 1, and I stick that all back in there, and I can look at these things, and I can see that that term is the only one I need to keep, and that this term is the only one I need to keep. And that tells me what lambda 1 and lambda 2 are approximately. And I go back. No, I'm going forward. No, I really lost. Sorry. Hold on. Now you've seen it all. Where am I? I must have gone through like 100 pages or something in one. Okay. So this is what I was trying to do. The maximum wave, the wave number of the maximum of the energy spectrum. Okay, and whereas Creighton says it goes to 0, as k max goes to infinity, I've just shown that it goes to root 2 ki. It doesn't go to 0. There is no, so if I use the same logic, and I'm not sure I should, there is no inverse cascade in this particularly low Froude number, stratified turbulence, okay? And I think a number of people spent a lot of time and resources in the 1990s looking for an inverse cascade in stratified turbulence. It was a suggestion made by Gage and Lilly. And worked on in numerical simulations that didn't show any inverse cascade. And a number of us here were involved in some of those.
So, but the data shows that the data is low Reynolds number, or this is all implicit analysis.
Yeah, but this is implicit, and it's just about statistical tendency, all right? So the statistical tendency is that it's not going upscale. So now it's the meat, okay? That's all fine, but that was all low Froude number, and it's maybe of interest for low vertical Froude number problems, as I say, an initial problem where you start off with vertical scale set by the initial condition. All right, so this is the problem. Let's say it's true initially. So let's say the evolution of the ensemble averages towards this is this equilibrium, monotonic kind of way. That's sort of the unwritten rule of this game. We can ask, does the system ever get there? And well, does it all hold? All right. So if I have a spectrum which is flat, my modal spectra, we're all independent of kz. And I'm actually doing a lot of this. It kind of depends on the kind of truncation I'm using. And I'm using cylindrical truncation. But if I use spherical truncation, the equations are all different, but the point is the result is the same. All right. So if I use this truncation, I know this is true, so this tells me what my energy spectrum is. And I can use some kind of way to characterize a vertical scale, or a vertical wave number, using that spectrum. Here's a kind of a classic one, but any one will do. They won't give you 4 there, they'll give you something else, but they'll all give you the same result. So I can define a Froude number like that based on my equilibrium spectrum. And it looks like this. And that's really bad news, because initially, this Froude number is actually this initially, okay? KB is buoyancy. I don't know if I ever defined that one. So that's N over U. U is just the square root of kinetic energy. So that's where I'm starting, right, with the Froude number, and that's where I'm winding up. Forget about the quarter. That depends on the details of what I did here, but it's going from, all you have to see is it's going from Ki to K max. So the vertical Froude number is getting bigger and bigger and bigger. And so even if this is true initially, it grows to be much, much larger values. evolution might have been initially in the regime of validity of what I'm saying here, but it grows out of it. Okay. So now what do we do? All right, and so that's about as far as you're going to go with statistical mechanics based on this quadratic approximation of PV. So now I'm switching over to simulations out of desperation. No, not really. I just wanted to point out something. This is a simulation, so we're not in the inviscid truncated stuff here. This is a real force dissipative thing. And that's the horizontal wave number logarithmically, and the vertical one logarithmically. And these are these normal modes. I was calling them geostrophic and ageostrophic, but now we drop rotation, and that word doesn't make sense, but there's a nice continuous limit from that to this. What's on the next page? Okay. So I already shown you that, at least if we start off with low Froude numbers, that this problem looks nothing like 2D. Okay, and here's my definition of miracle, which is that this spectrum approximately pops up. This is very early, okay, very premature, so don't write this down. This has been discussed in a couple of recent simulations, and much more work is necessary, and I realize that, okay? But the miracle is two things, if you ask me, is that there's no n in there. It seems to be independent of stratification. And that this epsilon is in there is also independent of stratification. And scales like this, and if the stratification is really strong, the horizontal velocity is way stronger than the vertical velocity. So that you could call that the horizontal velocity, it won't change it. And that's definitely horizontal length scale. So it doesn't seem to care what's going on in the vertical. And what I want to draw your attention to is that the horizontal spectrum and the vertical spectrum aren't living on two different planets, right? There are two ways of integrating this, okay? So if I want a vertical spectrum, I integrate in horizontal, and if I want a horizontal spectrum, I integrate in the vertical. So what we seem to be saying is, oops, that's not what we're saying. I really must learn the difference between up and down. So what we're saying is, I think I got these in the wrong order, is that if that's the modal energy in a Fourier mode, and we integrate it over the horizontal, then it gives us the vertical spectrum. And the vertical spectrum, as far as I know, this is what's going on out in the literature. And I've just given a talk last week saying I don't see anything like this in my simulations, so maybe I shouldn't be talking about it. But it seems that it has a piece. Now, I've said it was flat at large scales. And then there's this very classic gravity wave saturation spectrum, which comes from putting the Froude number, the spectral Froude number I described. So Froude number is vertical one, U over NH. So if you just take this for U, oops. And then H is just kz to the minus 1. And you just stick it to 1. And you're saying that the Froude number is 1 at every single kz. You'll get this spectrum, which is sort of considered the default best shot at reality as of today, as far as I understand. And I've said it's constant flat at large scales. Well, it must be this for them to be continuous at k equals kb. That's all there is to it. And then we also know that after the Osmodov scale, so the Osmodov scale, so there's two buoyancy scales. This is sort of the large one. If you come down from large scales, that's essentially where the Froude number starts to reach 1. And the Osmodov scale, in my view, is coming up from the isotropic small scale 3D turbulence. And you're coming up at a Kolmogorov spectrum, and you're saying, when will that cease to be any good? And that's epsilon cubed over n to the 1/2. That's KO here. So, at very small scales, it's isotropic 3D. Okay, and so that's my best idea of what the vertical. I mean, it's not mine. I think scientifically that's our best idea of what's going on in the vertical. So if I integrate my modal energy in the horizontal, I've got to get that. And if I integrate my modal energy in the vertical, I've got to get that with no n and no dependence on stratification. It's really strange, but it's not necessarily impossible. And I also want to point out that this is
it the same ranges you're integrating through?
my range here is 0 to infinity. So yes, but there's subtleties. There are subtleties here, right?
You different bits of the
But I've got all the bits. Maybe not. But anyway, I'm just blabbering out loud here, just so that everybody can disagree with it, and we can maybe get some discussion going. I want to point out that this is almost independent of epsilon, right? You see this spectrum looks very steep. So there's this Ki and Ko, flat, steep like crazy, and then Kolmogorov, and this K to the -3, and that's obviously flat.
What's the Osmondov scale?
This is the wave number.
I know, can you give me a number?
Oh, what you mean in a real fluid?
Yeah.
Oh, I know.
Atmosphere.
I think it's like 100 meters in the atmosphere. Is that what you're saying, Jim?
Numbers are in the ocean, it tends to be always around a meter. And the only measurements I've seen in the atmospheric boundary layer, strong stratification, is about a meter. In the upper atmosphere, it's probably about 10 plus.
Oh.
10 meters.
10 to 15
Okay.
meters, something like that.
Okay, so this thing
That's a
is
guess, though.
this thing is very justified then. It's almost independent of epsilon because that's not going to contribute much to the energy.
I mean, the way I figured it, since our data now matches this, is that
Your data matches this?
it matches the coefficient.
Okay.
What you have at the scales larger than the Osmondov scale is you have a cascade both of horizontal kinetic energy and potential energy, which are roughly in equal partition. Then once you get below the Osmondov scale, or you're approaching it, you have a cascade that involves horizontal kinetic energy again and vertical kinetic energy.
Right.
So the epsilon that you should have in there is going to be roughly the same over what? I mean, actually, we get a coefficient of 1/2 in of 3D turbulence. It's obviously 4/5. So, anyway, I have the arguments. When you look at the epsilon that's horizontal, it should be about a 2. It shouldn't be 4/5 epsilon. I'll show you later.
Yeah, okay.
Next week. I mean, we've got a lot to do for the rest of the day still.
Yeah, and I'm almost done, just a minute or two. What I wanted to show you is, based on what I've been hearing recently, I went and looked at a bunch of old graphs, so I haven't really generated anything based on what I've heard. I've looked at old stuff that was generated with other things in mind. But this is one of the ones I have for this 2D energy spectrum. And you'll notice that this looks like a box. All these kind of curves look like boxes. And that one doesn't, but this one does. So anything that sort of looks like that is conceivably not far away from a separable function. You can't have anything tilted, so this strictly speaking would be illegal. But if you just, as I say, this talk is cheap, and I don't think anybody's going to hold this against me. But if you look at this and you say, I'm trying to say tentative, close to a little bit on a good day, separable, right? Then I just need, essentially, if that's true, then I just need my vertical spectrum to integrate, be independent of n. And I need my horizontal spectrum to integrate, be independent of epsilon. That almost sounds like a miracle. But it's not, actually. I don't know if okay, so let me just, before I do that, let me just show you the issue about the vertical spectrum. The one I just drew, whoops, that's a bit steep. Okay, so that's K Osmodoff, K buoyancy. This is the one I'm calling N over U, and that's the one based on epsilon. Now, if I increase at N, keep everything else constant, what happens? Well, this is N squared, Kz to the minus 3, so this has got to go up. And what we're saying is, and then this is epsilon, and I can't change epsilon because epsilon is independent of stratification. And if it's not going to be independent of stratification, I'm not going to get that. So it has to fall down on the same, but that means that this is K Osmodoff primed at the larger N. And the only way I can get the same energy as this is to move the plateau down. Okay, and the plateau is actually just U cubed over N. And this actually does integrate and independent of N. So maybe it's possible. Now I have some other evidence that is kind of interesting. And this was something that we did, Mike Wade and I, looking at gravity waves. And the reason I'm going to talk about it has nothing to do with what we did it for. But one of the things we did was this is wave numbers, okay? And this is just, and unfortunately I think the nomenclature is all different, but this is just this smaller wave number is the one I don't want to talk about, which is this buoyancy wave number. And this larger wave number is the Osmodoff one. Okay, now if you look at the Osmodoff one, what's happening here is that we've measured it, statistically stationary force dissipated flow, for a bunch of N's, a bunch of different stratifications. And that's the Osmodoff scale we get. And as N gets larger, the scale gets smaller, the wave number gets bigger, we get this. Okay, now, look at this. 2 decades here, and 1, 2, 3 decades there. So if I connect them, I've got 3 halves, and it's parallel to the curve. Okay, it's in the world of numerical simulations of turbulence, it doesn't really get much better than that. So what does that mean? I mean, Osmodoff seems to go as a stratification of 3 halves. It says that epsilon seems to be independent of the stratification. Pretty good, actually. Now these are dissipation wave numbers. And all these are done on different numerical grids, which are written here. And as you can see, if I'm talking about these Osmodoff wave numbers, and they're larger than the dissipation wave number, they're not even resolved, okay? So you might choose to not believe me. It's just that these ones are resolved, and they're doing exactly the same thing. And as I change the grid, nothing's happening, they're staying the same. So there is kind of reason to be at least a little bit hopeful that this may be the truth. Okay, so that's it for the miracle. Oh, no, that's not it for the miracle. Okay, so if I want to integrate this and make it independent of N, I've got to have the plateau come down as N goes up. And I don't get that, okay? So what's happening is these are just N, and they're doubling every time, and this is a logarithmic graph. And so if this were happening, these curves would all be equally spaced. Okay, maybe a resolution issue, but the reason I chose that to focus on right now is that this isn't usually a hard part to resolve, right? This is the largest scales in the whole thing. So that does it. So I have some kind of positive results that I can show just digging up old results, and some negative. So 10 minutes to spare. Here's my punchline. No conclusions. It's much too early, but as I say, since there was a lot of talk about this subject and the two-timescale not being irrelevant, I wanted to make the point that the two-timescale analysis tells you where energy goes, and it tells you that it's going to itself become irrelevant, which isn't bad. And then
The two-timescale analysis. The 2 timescales be a rotation type scale and buoyancy time
yeah,
scale?
advective and 1 over the gravity wave frequency.
Oh, okay.
Right? So if you start off, the point is that most of these simulations that aren't being forced with high frequency modes wind up never generating any high frequency modes. And the reason is simple.
They never generated.
Yeah, right. Well, I just gave it to you. I mean,
Yeah.
we'll talk about it later. So I think
With
it's
stratified calculations, they're not giving high wave number frequencies?
not really high frequencies. Not a lot of energy in high frequency modes.
But I thought.
Like
it
2D
was-
modes, for example, and stratified turbulence have really high frequencies.
Which modes?
Two-dimensional.
Two-dimensional modes.
Yeah. So it's like a tube.
Well,
If you have
I
a
thought
tube,
stratified turbulence was going to, I mean, there's energy going to small scales,
yes,
right? If you have a minus 5/3.
yes.
Okay, so that should be generating high frequencies.
Well, no, wait a minute. You're talking about the range of scales of vortical frequencies.
Yes.
Okay. Yeah, like as in, the turnover time diminishes as
Yes.
as k gets bigger. Yeah, sure, no, that's fine, but that's all the slow time scale for me.
Oh,
I'm talking about high frequency wave time scales.
oh, high frequency waves.
Yeah, yeah. No, there's a,
Inertial waves or internal
Yes,
waves?
yes.
Inertial waves,
Yes.
oh, okay. So there's very little in the way of high frequency inertial waves,
yes.
Oh, that I accept.
Unless you put them in.
because, right, because you're supposed to be going to a large scale sort of geostrophic type of situation where all those high frequency inertial waves are sort of run out of the system.
So Joe Samaria also is, arguing about a composite spectrum, the Garrett and Monk arguments.
You mentioned that.
Have you seen
No,
that?
you told me that the day after he left.
Yeah.
Yeah, so I don't know.
You hadn't-
No, I haven't talked to him.
Okay.
No, no, it's true. I think I dropped the ball. I was supposed to email him, but I,
He's- thought he came up with something that would have all the right limits. An interesting way
What-
that, didn't
it can
really-
only be approximate, this miracle, but it could be a good one. But
It might be something.
But it's nice, I have this problem with this plateau not behaving the right way. I think that's very serious. But we'll see. It's still early days.
One question for you. This horizontal spectra being independent of buoyancy frequency, is that as long as it's stratified, right? So you're assuming n is sufficiently large and then at some point it becomes independent of n? Is that correct? Or is it independent of n regardless if n's small or
It's
large?
pretty, well, why would you answer that one? You're the one who said it.
I think the horizontal Froude number is small and kind of arbitrarily small due to perturbation analysis, and it kind of scales out of the problem with the lowest order. So the Froude number drops out actually.
We don't have a
And so
ton
the
of
dynamics-
results.
The lowest order dynamics become within the Froude number, and that's in.
Right. As long as Froude number is
Small, as long as the horizontal.
Horizontal
Froude number is
Froude,
small.
yeah, exactly.
Yeah.
Which is
Yeah,
u over n, right?
just put it in the L
Well,
where the H goes.
without rotation, U over N and L is horizontal. And probably stronger if it's U over N, if you bring in rotation.
But when you crank up the stratification, you have a problem with the dissipation getting in the way. So there's not a ton of results over a wide range of stratifications, right?
Might be a narrow.
Yeah. Anyway, let's all run over next door.